Hello everyone, welcome back to my YouTube channel. And today we are going to be continuing our Rust series. Particularly, we are going to be talking about ownership in Rust. So what is ownership in Rust? So ownership in Rust refers to some set of rules that governs how Rust manages memory. Unlike some languages with a garbage collector and explicit memory allocation, Rust uses a different approach. In this approach, memory is managed through a system of ownership, which are set of rules that are enforced by the compiler. If any of these rules are violated, the program will not compile, thereby ensuring safety without a runtime overhead. So the concept of ownership in Rust might take some time for you to grasp, but there's no need of being afraid or bothering yourself about that. The better you get at Rust, the easier it is for you to understand this concept, and the easier it is for you to write code that is both safe and efficient. So let's explore more by diving into a common data structure known as the strings. But before we do that, let's familiarize ourselves with three important rules of ownership. The first one is each value in Rust has an owner. The second one is there can be only one owner at a time. The third one is when the owner goes out of scope, the value is dropped. With these rules in mind, let's discuss variable scope. So I'll be taking you to my VS Code or code editor, and we'll be writing some code to explain what the variable scope is, and I'll be giving more explanation as to what the variable scope is. So now that we understand the three rules of ownership, um, let's now go into variable scope. In Rust, a scope is a range within a program for which an item is still valid. So we're going to be looking at this. I'm looking at this with an example, a string literal example. So I'll quickly clear this out and define a string literal. So I'll say let's s equals to. I'll save this and just going to look at three things, and I'm going to write in the comments to explain them. But the first is on this line, on line one, where we have the opening curly brackets. So in that point, S is not valid because we have not yet declared it. So we say S isn't so S is not valid here because we've not declared it. On line two, S is valid. So we can go ahead to do whatever we want in the body of our curly braces with S because it is valid. So we can just say do stuff with S. But after that, anything outside of the closing curly brace, and that signifies that the scope is now over and S is no longer valid. So this particular concept of variable validity within a scope is similar to other programming languages like JavaScript and the rest. So now that we understand this, let's introduce the string type and explore how ownership operates in a more complex data structure. So we're going to look at the string type. So here, I will just comment this out and I would say so unlike the string literal that we just saw, the string itself is a more complex data structure. And the reason for this is because it is stored on the heap. I touched on this in my previous video when I explained what the stack and the heap what they are. So this type of data is allocated on the heap, which allows us to store or allows it to store an unknown amount of text at compile time. The double semicolon here is an operator that allows for namespaces with the from itself, or the from function under the string type. So this string type can be mutated, as we'll be seeing in the example below. So I'll be showing you, giving you an example of that. So for instance, if we want to mutate this, we can use the mute keyword, or mut here, and say mut, and I'll come down to say s.push, and we'll say we want to push something like this. So this particular line will go ahead to print hello world for us. So I'll quickly run this program and show you what I mean. I'll open here, and so as you can see, we were able to mutate the string that is stored on the heap by adding hello world to it. So what is the key difference between string and string literals? Basically, it lies in how these types deals with memory. Understanding these key differences lays a solid foundation for comprehending Rust's unique features. In the case of string literals, as we saw on line 2, the contents are known at compile time, and the text is hard-coded directly into the final executable. This results in a fast and efficient string literal due to their immutability. However, the reverse is the case, or we face a different challenge, which arises when we start dealing with mutable, growable piece of text when using the string type. With the string type, memory allocation on the heap is required to support mutable and dynamic size content. And this poses two key requirements. The first one is that the memory must be requested from the memory allocator at runtime. The second is we need a mechanism to return this memory to the allocator when we are done with our string. The first part is accomplished by calling the string.from, that is the string and the double colon. This is an approach that is common in many programming languages. The second part differs between languages. In the languages with a garbage collector, memory cleanup is automatic. However, in languages without a garbage collector like Rust, it becomes the programmer's responsibility to manage memory deallocation. Nevertheless, Rust adopts a unique approach where memory is automatically returned once the variable owning it goes out of scope. The code on your screen illustrates this example. So with what we have on our screen, or what you have on your screen, when the variable s goes out of scope, Rust automatically invokes a special function called the drop function. This function goes ahead to execute at the closing of the curly brackets, ensuring that memory is managed properly. Take note that this pattern of deallocating resources is sometimes referred to RAII, which is short for resource acquisition is initialization, which is a very common concept for C++ programmers. This approach of memory management ensures a reliable and efficient system. Now that we've touched most of the aspect of the Rust ownership system, it is worth noting that the ownership system is not just a set of rules, but it is a powerful mechanism that ensures the safety and efficiency of our code. In our next video, we will be going deeper to explore how ownership interacts with function, as well as introducing the concepts of borrowing and references. If you loved this video, please like, subscribe, Thank you for joining me on this one. In case you have any issue with understanding stack and the heap, I'll be linking my previous video somewhere at the top, either here or here, I can't really say, but I'll be linking my previous video for you to catch up and understand what the stack and the heap is and how it plays a significant role in the ownership system of Rust. While you are at that, thank you so much for joining me on this one, and I'll see you in the next one. Peace.